Okay, so we'll solve some problem related to week 5 classes. So in week 5, sir has taught Van der Waals fluid and diamagnetism and paramagnetism. So we'll see. So we know for ideal gas, uh, the equation of state was like Cp equal to nRT. Right, this is for ideal gas. But in day-to-day life, we deal with real gas. Right. So for that, Van der Waals proposed some new kind of correction to this equation of state. Like he corrected pressure and volume. So previously for ideal gas, we were assuming only interaction of the particles with the wall. There was no interaction between two particles inside the box. But for real gas, two molecules inside a box, they will interact with each other, right? They put forces on each other by electromagnetic. So in actual case, they put force on each other. So for that, we'll get some correction to pressure, like m square a by v square, where this term represents the interaction between two particles in the box. Right. So we got a correction for pressure. So due to this additional term, the box will feel more pressure. Right. Due to additional interaction, this A is a constant that represents the interaction strength of the particles. So and V is the volume, and N is the number of particles. Right. So if number of particles will increase, then the pressure will also increase, and if the volume increases, then the pressure will decrease. Like I had a small box with volume V with pressure P, right? When this volume is increasing, then the particles inside it, they got more space. Then they will put less pressure on the wall. So in that manner, if volume is increased, pressure will decrease. So this part represents the interaction of the molecules between themselves. And for the second part, volume, we can't take this volume as it is, because the molecules inside the box, they have their own volumes also. So they occupy some volume. So to move around inside this box, they use the rest of the volume, right? If this A particle is occupying this volume, then this B particle can't overlap on this A particle, right? So for B particle, the available volume is this V minus some. Let's write this as VA, V minus VA. So the available volume for B particle is the total volume of the box minus the volume of the particles. So the actual volume for the system will be V minus NV. If there are n number of particles, then this B particle can't occupy their space, right? So the available volume for B particle will be the total volume of the box minus the total volume occupied by these molecules, right? So if there are n molecules and V is the volume of each molecule, this is the volume of each molecule, then if there are n particles, the volume occupied by this n number of molecules will be n times V, right? And if I take the difference, I will get the effective volume for the particles to move. So the equation will be modified to P plus m square A by P square times V minus m, right? So it's very close to the real gases. This is Van der Waals equation of state for the real gases, right? So we will use this in our questions. So the first question is, what does the parameter A denote in the Van der Waals equation? See, we have A here. A few minutes back I told you that this A parameter represents the interaction strength between the molecules. Right. So this is the strength of the interaction between the molecules. So we have to find it in the options. So A is volume per particle, no. Radius of the molecule, no. Kinetic energy of particle, no. This average attraction between the molecules, right? Coming to next question, the term in the equation of Van der Waals which determines the intermolecular force. So it's the same. This in the Van der Waals equation, the first term it denotes the interaction between the molecules. So they are interacting, means they are putting forces on each other. So this first term, this represents the force of interaction between the molecules. So we have the option here in question 2. So this is the right answer, right? Where this V minus NB, this represents the effective volume. Right. So next, let's go to next question. Okay. What happens to the Van der Waals equation when the pressure is increased drastically? So we have a box of particles with initial pressure P and initial volume P. As for real gas, Van der Waals gas, we are considering interaction between the molecules also. So the pressure part will be like this, right? But this volume, this the effective volume we have to take V minus NV. As pressure is increasing, the volume will decrease, right? So the effective volume should change due to the increase of pressure. So instead of writing like this effective volume which is a constant, we can write a V which is a variable now. So the first option is the right one, right? If we don't consider interaction between the molecules, then that's the case for ideal gas. then this is the right answer, PV equal to NT. And we are saying the pressure is increasing, and the volume also will change, but it's always constant if it is effective volume, so it's not also right. So the right answer is this. Okay. Coming to the next question. For a van der Waals gas, the reduced volume is 5/3, reduced temperature is 3/2, then find the reduced pressure. Right. So what we are given, the reduced volume, this is 5/3, and reduced temperature is equal to 3/2. So we have to find reduced pressure. So initially we have the van der Waals equation in terms of P and V, right? Let's omit the R term, then 90. So this is P plus m square A by E square V1, right? So what is this reduced volume, reduced temperature, and reduced pressure? This is the coefficient when we the coefficient of critical volume, critical temperature, and critical pressure. Like we define VR as total volume divided by this critical volume. Similarly, we define TR as total temperature divided by this critical temperature. Similarly for pressure also. Right. What are these critical volume, critical temperature, and critical pressure? These are the points where the phase of one state, like if we consider gas and liquids, uh, if we consider gas and liquid, let's assume temperature is a variable here, and we have, let's assume this is a box and these are water, this is liquid state. So as we increase the temperature, heat will go to the system, and this the temperature of the liquid will increase, right? And eventually eventually if we keep on giving heat to the system, then what will happen, the temperature will increase, then at a certain point the temperature will heat to, if we assume this to be water, then temperature will heat to 100 degrees Celsius, and at this point the temperature won't increase anymore, even if you give more heat to the system. Why? Because this, for water, this 100 degrees Celsius is the critical temperature. What happens at this temperature? At this temperature, the phase of this molecule changes. What does that mean? That means the water will go from liquid to vapors. So at this critical temperature, the phase of the system changes, right? And it will keep on this temperature will remain as it is as long as all the liquids will be vaporized, right? So what is this critical values? At these critical values, the phase of the system changes. It will go from one phase to another phase, right? And we can derive this critical temperature, pressure, and volume from the van der Waals equation itself. We can take two variables like pressure and volume for initial, case, and we assume temperature is constant initially, right? Then from the saddle point method, we know they will hit a maxima if we keep on increasing pressure, then and volume, keeping the temperature as constant. That means if I keep on changing pressure with respect to volume, then it will hit some maxima. Let's say this is PC and PC. At this point, this function is maxima. That means this derivative will be 0, right? Like this is the initial equation, and I keep on changing the pressure and volume, keeping the temperature constant. So let's think an arbitrary function of this, like this this is volume, this is pressure. The pressure will keep on increasing, and the volume will okay, we can think about this. Initially, if we increase pressure, what will happen? The volume will decrease, but at a certain point, what will happen? The pressure will hit a critical value, and it won't go down on that, and the volume will also hit a critical value, and it won't change after this point. So after this point, what will happen? It may change its trajectory. So we'll get some saddle points. It may be minima, maxima, or something like this, where this derivative is 0, right? Where this critical volume will touch, like if we have n number of molecules with molecular volume NV, then if I keep on decreasing the volume inside the box, initial volume is V and the molecules volume are NV, so the effective volume is V minus NV, right? So if I keep on decreasing the volume, so this V value will hit this molecular volume, right? So I can't compress this box below this molecular volume. I can't reduce the size of the molecule. So this is the finish point. So something like that you can think about it. So I have one condition that from saddle point method, that pressure, the change of pressure with respect to volume will be 0, and the second derivative will also be 0. So I can find a term, I mean I can find a equation with in terms of P. Like from this equation I will get NT over V minus NV minus N square A over V square. So I got P. Now I have to do the derivative with respect to V. So initially I am doing this to derive the critical temperature, pressure and volume, because we will use this in next question. So I am doing this in this question itself. So be with me for this. So I have this pressure as NT over V minus NV square A over V square. So I have to find dP over dV at constant temperature, right? So what will happen to the first term? This will be minus NT over P minus NV whole square minus it will be plus 2n square A over V cube. So I got del P over del V, which will be 0, right? And then I can find del square p over del v square, which will be minus minus plus, so plus 2 and t. I am just applying chain rule, v minus nv to the power q minus 6 n square a over v to the power 4, which will also be 0. So from this equation you can find this term. I am equating this to 0, so I will get 6n square a over v to the power 4 as 2nt by v minus nv, right? And from the first equation I have minus nt by v minus nv whole square equal to plus 2n square a over v to the power q. So you see similar terms here and here. I can do one thing. I can take this v to here, 1v to here, and 3 to downstairs. Then I will have 2n square a over v cube as 2nt over 3 v minus n, right? So I can put this term in this equation. Then what I will get, this is nt over v minus nv whole square. This is this one v here. So this is 2nt v 3 v minus nv. So to find this critical value, that means these will be constants, so they should not depend on any of the variables. So I need to find a equation like in t, p or v, which will be constant. What are the constant values? N, v and the numbers whatever I have. So if I solve this on the both sides, I can cancel this square, this will go. So effectively I'll have oh, sorry, this was cube, right? So this should be cube also. Okay, sorry. So I can put it here. This is cube. So this whole square and 2 will go. So this is v minus nv. So this will be v over 3 v minus nv equal to 1. So this is 3 v minus nv equal to v. So effectively what I have, 2v equal to 3 and or v equal to 3 by 2 and so you see this volume is independent of other variables. What are these? Number of particles, and this is the volume of each molecule. So these are constants. So I got a value for this volume which is constant. So I can call this as critical volume. So I see the critical volume is 3 by 2 NB, right? So we need this value for our solution. So similarly, I have to find TR and PR also. So I can apply this VC equation in this equation, right? Then I'll get a term in terms of T, because there is no P dependency here. If I put the V value here, I'll get some terms in terms of, I'll get this temperature in terms of some constant. So let's put this V value here. So let me write down this equation again. This was del P over del V, which was minus NT over V minus NB whole square plus 2n square A by dq is equal to 0, right? Now I have BC, so I can put this in this equation, then I'll get some constant value in terms of T. So let's do this. This is NT, B is 3 by 2 and B 3 by 2. Okay, I have made a mistake here. There was 1 2 here, so this is 2, this is 3n, right? So 3NB minus NB we need this critical value for our solution, so just be with me until this derivation. So this B is 3 NB minus NB whole square plus 2n square A over B is 3 NB is equal, because there is a minus here. If I take to right hand side, it will be plus. So what we have then? We have NT over 2NB whole square, so 4, then NB whole square, and from the right hand side we have 2n square A over 3 to the power 3 is 27, then NB cube. So this square and cube will cancel and one n will go. So effectively we have TC as 2 into 4 Na over 27 NB. So this n also cancels, so it's 8A over 27B. Yes, right. So TC is 8A over 27B. Right. Now we need only PC. So for PC, I can use the Van der Waals equation, like P plus n square A by B square into B minus NB equal to NT. So I have BC and TC. So if I put those values here, then I will get PC, right? So let's write this as PC, and let's solve this first. Okay. So P will be NT over V minus NB minus N square A over B square, right? So BC is 3NB and TC is here. So PC will be N times TC is 8A over 27B by this is 3NB minus NB minus N square A over B square of B as the put. This is 3NB whole square. So the PC value will be, this is N 8A over 27B into 1 over 2NB, and cancels, 2, 8 cancel, 4, and from the second term N square cancels, so A over 9B square. So I have 4A over 27B square minus A by 9B square. So this is 27B square, 4 minus 3A. So PC is A over 27B square, right? So I have all this PC, this is 3NB, and TC is 8A over 27B, right? Now what is given? We are given the reduced volume, reduced temperature, and reduced pressure, right? So this reduced pressure, this is defined as total pressure divided by critical pressure. So this I can write as the total pressure as PR PC. Similarly, I can write V as VR BC and T as TR TC. So we are given these values, and we got these values by solving the above equations. Now put all these values in the van der Waals equation of state, then we see P plus N square A P square B minus NB equal to NT. So P is PR PC plus N square A over B is VR BC whole square, then B is VR BC minus NB equal to N into TR TC. So we have these critical values of these parameters, so we will put these in the above equation, then we will get PR PC is A over 27 B square plus N square A divided by VR square, then BC is 3NB, so 3NB square, then VR is there, then BC is 3 NB minus NB, and in the right hand side we have NTR, and TP is 8A over 27B. So when we solve this, you can check it, because this derivation already took so long, so you can check. It's simple. We will get a equation in terms of reduced parameters as PR plus 3 over VR square into VR minus 1 over 3 equal to 8 over 3 TR. Right. This is the van der Waals equation in terms of reduced parameters. So we are given these values. We are given VR and TR. We need to find PR. So let's check once again. Okay, VR is 5 by 3, TR is 3 by 2, and let's find some white space here. Okay, VR is 5 by 3, TR is 3 by 2, and we have to put these values in the reduced equation. TR plus PR plus 3 over PR square into VR minus 1 over 3 equal to 8 over 3 TR. So we have BR and TR. Now for these values, we'll have PR value as, let's put this first, 5 over 3 whole square, then, oh sorry, no, sorry, okay, 5 by 3 is there. Okay, 5 by 3 minus 1 over 3, then on the right hand side 8 over 3, TR is 3 by 2, 3 cancels, 2, 8, 4, and from this side we have PR plus 3 cube by 5 square. This is 2 over 3 equal to 4. 2, 4, 1, 3 I can cancel here, so this is 6 square. So PR plus 9 over 25 is 2. So PR will be 2 over 9 over 25. If you can remember this equation, then you don't have to do all this. So as we are doing this first time, I just derived all this, right? So this is how much, and this is, there is some mistake I think. Oh, this is 5 minus 1 is 4.
4.
Yeah, sorry. So that should not be any 2. So this is 1. So 1 minus 9 over 25. Okay. So this is 25 minus 2. There is a mistake. Oh, sorry. I cancel this 3 and 3 here. I can't do this, right? this is one term adding to another term. So this is x, so this is 3. 4 cancels, so this is 3, so this will be, let me erase this, so mistakes. This is 3 cube 27, so this is 3 minus 27 over 25. So this is 75 minus 27 over 25. This is 8 and 48 over 25. This is our answer. So here you see there are 48 over 25. So as this is tutorial, I just derived all of this. You don't have to do all of this. Just you have to remember the reduced equation if you face this kind of problem in your exam, right? So this is the answer, 48 over 25. Now see, I already told you those solving will be used in the next question. We are asked what is the pressure of the van der Waals gas at critical point. So we are asked PC. We derived this sometime before. PC is
A by 27.
Yes, A over 27. Okay. Now coming to the next question, which is related to magnetism. So the question is, materials with spinless charged particles under an external applied magnetic field shows which behavior? Paramagnetism, diamagnetism, both or none. So we have a material which do not have free electrons. This spinless charged particles, metals with spinless charged particles. Spinless means there are no free electrons inside this material, right? Like we have an atom and the electrons are revolving around this in some orbit, then orbital. They are arranged in orbital, some S, P, D, F orbital. So in that orbital there are no free electrons. That's why we are calling it as spinless, right? So the electrons are always in pair state inside this molecule. So in that case, if an external magnetic field is applied, then what will happen? As there are no free electrons, like if there is one electron like this, then we will consider this atom's spin is half integer, because we have one free electron which is there alone. If two electrons are there, then their spin will cancel each other, then effectively we have spinless molecule, right? So we have spinless charged particles. Then we are applying this magnetic field. Then what will happen? You know what is this law? Probably Lenz is law, right? Maybe I don't remember the law. If we apply a magnetic field to a material, then it will induce its own magnetism due to this applied magnetic field. Why this happens? Let's see. If an electron is revolving around this nucleus, let's assume like this, then we apply external magnetic field H, then this will then the electron inside this molecule, they will arrange themselves, like they are rotating around some molecule, right? There this electron, it has a charge plus E, right? So a charge particle rotating inside a circle, in a circle, will induce what? A magnetic field of its own. So it will induce its own magnetic field due to the motion of the electron around the atom. So if we apply external magnetic field, then what will happen? These electrons will move like this, so that the induced magnetic field, it will oppose the applied magnetic field. Right. This is I don't remember whose law is this, and this induced magnetic field is purely due to this orbital angular momentum of the electron. Right. If spin is there, then it will have some other kind of magnetic field. Spin is intrinsic, so we can't imagine it to be moving around circle. So it's some intrinsic property of a particle. So if spin is not there, then the only contributor to the induced magnetic field is orbital angular momentum. And from maybe from Lenz's law, the induced magnetic field always opposed to the applied magnetic field, right? So then in that this behavior, what is this behavior? We are applying a magnetic field, and we are getting opposite magnetic field from the atom, which is opposite to the applied magnetic field. So in that case, what will happen? They will repel each other. So which magnetism property is repelling? This is diamagnetism property. Yeah. If some unpaired electrons are there, then they will align themselves in the applied magnetic field. So in that case, some paramagnetism will induce. That means the atoms, they will align along the direction of the applied magnetic field. So if this is small, then we will call it as paramagnetism. So as we don't have any free electrons, so in this case our answer is diamagnetism. Right. Then coming to the next question. So the question is a diamagnetic rod is suspended in two poles opposed to magnet, and its line is based to the direction of magnetic field. So we have a diamagnetic rod, and it is suspended between the two poles of the opposed to magnet, right? So let's assume this is north and this is south, and fields are going from this direction to this direction. So what will happen to the rod? As we know, the diamagnetic materials, they repel from the magnetic field. So as this rod is there inside this, let's assume this is the direction of the magnetic field, and this diamagnetic rod is sitting like this. So, and let's assume this magnetic field direction is this way. Whatever it may be, magnetic field direction, it is always repelled. Like a ferromagnet, like iron, it will always be attracted by a magnet, right? Similarly, a diamagnet, whatever the pole of the magnet is, it will always be repelled by the magnet. So what we have north or south here, it doesn't matter. it will always be repelled. So this part of the rod will be repelled by this, and this part of the rod will be repelled by this. So eventually what will happen, inside this magnetic field, this rod will be like this, in this position, where on both the sides the magnetic field are equally repelling this diamagnetic rod. So what is the answer then? This rod is then perpendicular to the applied magnetic field. This positive magnetic field. So we are applying the magnetic field through this positive magnet on this diamagnetic rod. Then the situation will be the equilibrium situation will be like this rod will be perpendicular to the applied magnetic field. So the answer will be this. Right. So it's clear, right? Then coming to the next question. If magnetic field is applied to a diamagnetic liquid in a U tube, the liquid level is in that arm is this. So what is the situation here? We have a U-shaped tube. Right. And we have some diamagnetic liquid inside this. So initially it was in this level. Let's name this side A and this side B. Then what happens? We have to apply a magnetic field on this side A, right? Then what will happen? As this is diamagnetic material, as we apply magnetic field on this side, this will get repelled, right? So what will happen on this side? The level will decrease. This will come to this level, let's say. Then in this side the level will increase. So on the side where we are applying the magnetic field, the level will decrease. The level in that arm will decrease, right? You got it, right?
So that means the applied field has no effect on the other arm.
This will we are assuming. Let's assume the other arm is very far from this magnet. Yeah. Ideally,
I thought it could be remains the same at
sorry.
the end. I thought it could be remains the same. That's why.
No, it's saying one arm, on one arm we are applying magnetic field, so it won't remain. If we are applying magnetic field on both the arm, then it will balance to each other, then nothing will happen. But we are applying on one side, that's why the other side will go. Okay. Okay. The next question is, susceptibility of a diamagnetic substance is this: small positive, small negative, large positive, large negative. So what is susceptibility? This is the ability of the material to magnetize due to the response of applied external magnetic field. So if we apply external magnetic field on a material, then what will happen? Some induced magnetic field will be there, whether it will be opposing or it can be in same direction, whatever it may be. but some induced magnetic field will be there, right? So we measure this effect in terms of magnetization, and the magnetization per applied magnetic field we define as susceptibility, right? Means how easily this material is magnetized due to the effect of external magnetic field is called susceptibility. So for diamagnetic case, what will happen? As we are applying external magnetic field, it will induce opposing magnetic field. So the direction of the induced magnetic field will be opposite to the external magnetic field. So the susceptibility direction, it should be negative. Means negative to this applied magnetic field. So one negative sign should be there. And diamagnetism is there. So what happens in diamagnetism? Like there are no free electrons, no unpaired electrons. Free will be the wrong word. No unpaired electrons in that system, in that atom. Then there is no consideration of spin contribution uh, to the induced magnetic field. So in that case, only the orbital angular momentum will contribute to the induced magnetic field. So you see, only the orbital angular momentum is contributing now in the absence of speed. So it will be always less than the combination of L plus S, right? We have some unpaired uh, electrons in atom, then its spin will contribute to the induced magnetic field, and it's revolving around a nucleus, then its orbital motion will induce the magnetic field. So the total induction of magnetic field is more than the single orbital case, right? So in that case, it will be smaller than this spin plus angular momentum case, as we are considering only uh, angular momentum case. As we are taking the example of diamagnetism, that means there are not much free unpaired electrons, not free, unpaired electrons. So only the angular moment, orbital angular momentum is contributing to the induced magnetic field. So its induced magnetic field will be of small magnitude. So the susceptibility will be small, and it should be negative, as it is diamagnetism. Its induced magnetic field will be opposite to the applied magnetic field. That's why it's negative. And as only the orbital part is contributing to the induction of magnetic field, so this susceptibility will be small. So the right answer is this one. Any questions on this?
It's okay, sir.
Okay. Then we'll go to next question. Select the statement which is not correct in case of change in temperature of metal. So what are the statements we have? Diamagnetic substance loses their magnetism on removal of external magnetic field. That's correct. As you know, you are applying external magnetic field on a diamagnetic material. As long as you are applying the external magnetic field, it will keep on inducing its induced magnetic field opposite to the direction of the applied magnetic field. As you switch off this external magnetic field, then it won't give response to the external magnetic field, so its induced magnetic field also will go to 0. So this is correct. Then the next one is when placed in a uniform magnetic field, they tend to move from weaker part of the field to stronger part of the field. So let's draw this as uniform magnetic field, and it's smaller here, and it gets stronger on this side, right? And we have a diamagnetic material inside it. So diamagnetic material is always repelled by this external magnetic field, right? So we have strong magnetic field from this direction, right? Let's draw the arrow. Like uniform magnetic field is there, and let's assume the arrow goes like this from smaller to weaker side. Let's assume. Okay, let's put that aside. So we, in essence, we have stronger magnetic fields from this upper side and smaller magnetic field from the lower side. As this is diamagnetic material, so it will be repelled by the magnetic field. It will be repelled by this side also, and it will be repelled by this side also. But as this side is stronger, magnetic field is stronger on this side, the repulsion from the upper side will be more compared to the lower side. So this diamagnetic material will eventually move to the weaker magnetic field side, right? So the statement says in a non-uniform magnetic field, they tend to move from weaker part of the field to stronger part of the field. So this is not true. It's not moving weaker to stronger. It's moving stronger to weaker side. So this is wrong. Then the next one is diamagnetic substance has negative value of susceptibility. That's correct. We have seen this in previous question. Negative susceptibility means it will oppose to the applied magnetic field. The induced magnetic field will oppose to the applied magnetic field. So this is correct. This is correct. This is wrong. So the last one is the all of the above statement is not correct. That's not correct. Two are correct. One is wrong. So this is wrong and this is also wrong. Okay. Any questions on this?
No, sir.
So we move on to the next question. Just give me 1 minute. Okay. Coming to the next question. Consider a substance with SL over Sg as 3 by 2 and Bl over Bg as 3 by 5. Then which of the statement is true? What is this SL and Sg? This is the entropy. Liquid, and this is the entropy of gas, and these are volumes of liquid, and this is volume of gas. So uh, um, and as in Vanderbilt class, it has been taught like at constant temperature, the change in pressure by volume. Just some what it's called. Okay. Okay. Uh, in phase space, in pressure versus volume space, there will be some curves representing the behavior of the material. For material, we mean liquid or gas. We do not deal with solids. So, as we expect that for a particular temperature, constant temperature, the pressure as the pressure decreases, the volume will increase, and as the volume decreases, the pressure will increase. This is the curve in phase space. So this is with a particular temperature. As we keep on changing the temperature, let's say that some this is T1. At some T2, the curve will be getting different. But at a particular temperature, let's say at a critical temperature, what will happen? Uh, the curve will go like this, and it will remain constant. So as the volume goes changes, but the pressure will not change. This curve is for critical temperature. That means what happens at this critical temperature? Uh, if we assume liquid to gas case, this liquid uh, state changes to gaseous state. So in this case, what happens? The volume of the system increases as the liquid is going to gas. It will occupy more volume, so the volume keep on increasing at this critical temperature, but the pressure exerted on the wall will not change. Right? As we go temperature below to this critical temperature, then what will happen? Its behavior will be like this. So you see this region as the pressure decreases, the volume it should increase, but the volume is also decreasing. You have seen this from the class. For temperature below Tc, we will have some curves like this. Right. So you see in this region, as the volume increases, the pressure is also increases. Normally, the pressure and temperature, they have inverse relation. Sorry, pressure and volume, they have inverse relation at a constant temperature. But in this region, what is happening? They are linearly dependent now, pressure and volume. So this is below this critical temperature, right? So for that we can draw some approximate line to interpret that from this region the state of the system can be in both states, and that means the molecules can be in liquid state or they can be in gas states in this region. So in this region they are in liquid state, and in this region they are both in liquid and gas state, and after some distance they will go to gas states. So this region, this is the critical region for a temperature below critical temperature. So from that, we got some formula from class, like change of pressure with respect to volume is the ratio between the uh, this entropy, which is the difference between liquid and gas, and volume, difference between liquid and gas, right? So we have this kind of formula from the class. Then we see we are given SL over SG as 3 over 2. So can I write like SL equal to 3 and SG equal to 2? Can I write this? Anyone? No, we can't write, because we are we are deriving this from the ratio. Then we can have situation like SL can be 6 and SG can be 4. In that case also, SL over SG, they will have the same ratio, 3 over 2. So I can't write SL as 3 and SG as 2, but I can write as SL as 3x and SG as 2x, where this x is some arbitrary number which will be multiplied on both SL and SG, so that this ratio will always be same. Let's see, 3x over 2x. We don't know the x value, we do not have to know also, we just need to solve this equation. So I can write SL as 3x and SG as 2x, right? Similarly, from the other ratio, VL over VG, I can write VL as 3x and VG as 5x, right? Then we can put all these values in the formula. Then what will they have? Let's see. So we have del P over del G as SL minus SG. So SL is 3x minus SG is 2x divided by VL over VG. VL is 3ax and VG is 5x. So how much I will have? X over minus 2x. So it's minus 1 over 2. But what I can see here, the slope is negative now. That means pressure increases with increasing temperature. Okay. So with respect to temperature, right, we'll derive with respect to volume. Okay. My mistake. This is del P over del T. You can check from the class. This is not B. This is del P over del T. The change of pressure with respect to temperature is having this form, right? Then we got del P over del T has negative value. That means what? We are having negative slope. So this is P and this is T. As the pressure increases, temperature will decrease. Right? Negative slope means this. Positive slope means this. So we have negative value, so we have negative slope. That means these two parameters, they will show opposite behavior. So the what is the right answer? Pressure decreases with the increase of temperature. Right. Okay. Then coming to the next question. Okay, the question is the Landau diamagnetic susceptibility and Helmholtz free energy are related by which equation? Okay, for that we need to know the relation between magnetization and Helmholtz free energy. Uh, Helmholtz free energy is a parameter in canonical ensemble. So for canonical ensemble, we can derive magnetization in terms of Helmholtz free energy. Helmholtz free energy, I should give some different notation for applied magnetic field. Then let's write it as HM. This is applied magnetic field, and this is Helmholtz free energy. Then what is the relation between this MH and HA? The relation is okay. We don't have to denote this Helmholtz as H. We can write as F. F is Helmholtz free energy. So the magnetization is in terms of Helmholtz free energy del F over del H, where this H is applied magnetic field, right? And this F is a function of this applied magnetic field. But we don't have F in the option, so we need to expand this in this F in terms of Taylor series. So this magnetization, this is a function of this Helmholtz free energy, like this relation, and this is per volume. So this magnetization is 1 over V del F over del H. This is magnetization like per applied magnetic field per volume, right? Then we know this susceptibility formula as magnetization per unit applied magnetic field, right? Then I can write this del F as F over H if it is not very small. This is F over H. Then we can expand this I can take this H to the left hand side, which will be MH equal to F of H over V. Then I can take derivative with respect to H on both the sides, as we need some F double prime. So I need to take derivative with respect to H, as the F is a function of H. So from the left hand side I'll have M, and from the right hand side I'll have F prime H over V. right. uh, if we consider it to be diamagnetic, then the induced magnetization will be opposite to the uh, applied magnetic field, so one negative sign will come, right. So we get a form like f prime h over v. So when we check the options, we don't have f prime h, we have f prime 0 at point at 0 applied magnetic field we are getting susceptibility like this. So this is not the option, so we need to expand this f prime h. So we can use Taylor series, like for a function f of x, we can if we apply Taylor series, it will be like f of 0 plus x into x by 1 factorial f prime of 0 plus x square by 2 factorial f double prime 0, and so on, right. Now my f of x is this f prime h, right. Then I need to Taylor expand this f prime h. Then what I will get for f prime h, if I expand this around h equal to 0, I will get f prime of 0 plus, as this x is h now, then this is h, then one derivative, then it will be second derivative of f of, and it is at 0. So for f prime of h, I will have f prime of 0 plus h into f double prime of 0, right. And from saddle point formula, we'll have del f over del h as 0, so this term will vanish. So effectively I'll have f prime of h as h into f double prime 0. If I put this here in this equation, I'll have m equal to minus h f double prime 0 divided by b. Then I can take h to the denominator here, then m over h, what is this? This is susceptibility. This is equal to minus f double prime 0 by v. So what is the answer? This f double prime 0, this will be minus of v susceptibility. So what is the answer then? Here, this is the answer. Did you understand this, right? Any questions on this? We started from simple definition of magnetization. Then we defined susceptibility in terms of magnetization. Then we saw that there is no f term f in the answer, so we need to do the derivative on the f. So what we did then, we took the derivative with respect to h on both the sides. Then we got one f prime here, but still there is no f prime h on the answer side, so we Taylor expand on this f prime, as there are zeros. This f should be a function of 0, so we need to Taylor expand this f prime around 0. So we Taylor expanded this, and from the saddle point approximation, this first derivative is 0. Then we will have this f prime of h as h f double prime. So we can substitute this, and finally we are getting this f double prime 0 as minus v chi of n. This is the answer. Right. Any questions on this? Okay. And this is the formula for canonical ensemble. As in canonical ensemble, we have Helmholtz free energy instead of the internal energy. Right. Then coming to the next question. Okay. The question is the effective number of Bohr magnetons at high temperature in pyromagnet is given by what? Okay. So from class we got for polypyramagnets the susceptibility formula as 1 over 3d J into J plus 1 n this G mu B also. But this G is Landau G factor. This was for high temperature. You can check from the class. This is susceptibility formula for high temperature. You had some X term which was dependent on beta and magnetic field. So high temperature means small beta or small applied magnetic field means we will get this X was going some function of B, and this susceptibility was dependent on this B with some other factors, right? From the class I am trying to recall. So this X was dependent on B and H like this. So sorry, beta and H. So beta, what is beta? Beta is 1 over T. So small beta means high temperature or small magnetic field. That means you will get same effect as high temperature if you apply only small magnetic field, and inversely if you apply small temperature then you can get the similar effect by applying high magnetic field. This is from class. So from that, for the high temperature term we were getting susceptibility as this term. So you see there is a Bohr magneton term here. So whatever the coefficients with this will be magnetic moment. What is Bohr magneton? This is a measure of magnetic dipole moment. So usually we take Bohr magneton as a unit of magnetic dipole moment. So whatever the coefficient with this, we can take that as the magnetic dipole moment. Magnetic dipole moment mu. So we can see we can leave the number of particles and temperature as it is. Then the rest of the term I can pull this inside this square term. Then what I will have? I will have J into J plus 1 into G mu B whole square. So you see the coefficient of mu B is this term. So this is the magnetic moment. Mu is G times square root J into J plus 1. So we have here, this is the answer. This is from susceptibility, or you can do the derivation from quantum mechanics. I just took a shortcut from this susceptibility. I just had to show you somehow how to derive. And very fundamental. From fundamental means you will get this form. You don't have to consider susceptibility. But in this case, it is giving like high temperature, so we need to take the susceptibility condition. Similarly, if you have low temperature, then there is some susceptibility um, form also, which is uh, linearly dependent on J. So you can take the coefficient of mu b as magnetic moment. So in this case, the magnetic moment will be linearly dependent on this J, not the root over. So this is for low temperature. This will depend on J linearly, and there is some Landé G factor, so mu will be G times J at low temperature, but for high temperature this is a power. So just remember this, we'll use this in next question. High temperature means if it is room temperature also, this formula is valid. Low temperature means near to absolute zero, so we don't have many use of this formula for room temperature question. So coming to the next question, here you are given a general form of Landé G factor formula, which is this G equal to 1 plus this term, where the symbols have their usual meanings. Where this S means this is the total spin of the system, J is the total angular momentum, this is spin momentum, this is orbital angular momentum, this is spin angular momentum. So we are given two ionized atoms, Nd3 plus and Cs3 plus. Then we have to calculate the magnetic moment for these atoms, right? So we are given a hint for this Nd3 plus. We have the distribution of electrons like this, where this Xc means this is the stable atom. After this we will have some additional configuration for this Nd3 plus. You know, xenon is a stable element. That means there is no unpaired electrons in its orbital. All the electrons are paired, and for Nd we will have some 3 extra electrons in the F cell. So you might be remembering from 12th class, we have some cells around a nucleus where this electrons will be distributed. So each cell, they are also degenerate. The cells are the cell or orbit. This is composed of some subcells or orbitals. So we call this orbitals as, we name these orbitals as S, P, D, F, G, and so on. So we know the capacity of each orbital. Like we know if there are 3 electrons in an atom, then they will occupy the first state S. So they are distributed like 1s, then 2s, then 2p, something like that. So p has capacity of carrying 6 electrons. So it has 3 energy levels, and in each energy level it can keep 2 electrons at a time, one spin up, one spin up. This is for P. And for D we have 5 subcells. So this each cell can store 2 electrons with opposite spin. So it can store 10 electrons. So similarly for F cell we have 7 subcells, not cells, it's suborbital. This is orbital, these are suborbital. So we have 7, 2, 3, 4, 5, 6, 7 orbitals for F orbital. We have 7 suborbitals. So we are given for this atom Nd 3 plus. What does this mean? This atom is ionized. That means it has we have taken 3 electrons out from the atom, so it is ionized now. So in this system we have 3 electrons in the 4f orbital. So this 4f orbital, it has 7 suborbitals, 3, 4, 5, 6 and 7. So this each orbital have some specific angular orbital angular momentum. So there are 7 suborbitals, so angular momentum will go from minus L to plus L. So we can, for F we have plus 3, plus 2, these are L values, plus 1, 0, minus 1, minus 2, minus 3. These are the orbital angular what we call this quantum number value for this L. So we have 3 electrons in this F orbital. So from the rules we need to arrange them as they all are empty. We can arrange them one at a time, one in each suborbit, starting from the lower. And they are all degenerate states. So, but from rule we need to fill from left to right. And as there are, we cannot fill 2 electrons in each suborbital as long as the whole suborbital is filled. That means I cannot do this until all the electrons are occupying the degenerate energy levels. Right. This is from Pauli exclusion principle. No 2 electrons with same states are allowed to sit on the same energy level. So to sit to come another electron, it has to flip its spin to sit on the same energy level, so that the states will be different for these 2 electrons. So for this case we have 3 unpaired electrons for this Nd plus atom, right? And we have 7 suborbitals, 3, 4, 5, 6, 7. This is L value plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus. So I have 3 unpaired electrons, so I can arrange them like this: 1, 2, and 3. Right. Then for this system, this is for Nd 3 plus. This is the last orbital. Before this, all the orbitals will have like electrons paired in each of the cells, right? So this is the last orbital where the electrons are arranged like this. So from this Landé G formula we can say this total angular momentum, this can be L plus S or this can be L minus S. when this will be L plus S, when the number of electrons occupying the states are like, how to say this, if there are 7 suborbitals and there are 4 electrons occupying the cells, that means more than half of the cell is occupied, then in that case we'll have J equal to L plus S. If less than half of the energy level is occupied, like in our case 3 are occupied out of 7, then in that case J will be L minus S. Right. This is when more than half of the energy level is occupied. And the second one is less than half of the energy levels are occupied. So for our case we have 3 unpaired electrons and 7 energy levels. So this is plus 3 plus 2 plus 1 0 minus 1 minus 2 minus 2. These are L values, small l values. So from these we can calculate the total angular momentum as sum of these all L's. Like I have 3 unpaired electrons in these 3 states, plus 3 plus 2 and plus 1. So what will be the total angular momentum? Sum of all these 3. So 3 plus 2 plus 1 is 6. So similarly I can calculate the total spin as I have 3 unpaired electrons, each with spin half. So all are in different energy cells, so they can be in all half states. So total spin will be half plus half plus half. So 3 half. So I have L, I have S. Now it's time for J. What will be J? You see, they are less than half of the energy level is filled. So J will be L minus S. So what is this J value? And 6 minus 3 equals 2. This is 12 minus 3, 9 over 2. So I have J, I have L, I have S. Now I have to calculate this Landé's factor. I have to just put these values in the formula and I will get the Landé's factor. But the ultimate aim is to calculate magnetic moment. You remember the formula we discussed previously here. The magnetic moment is G times root over of J into J plus 1, where this G is Landé's factor. So first we have to calculate this Landé's factor, and J we have, so the only remaining is Landé's factor. So we will calculate this and we will put this directly and we will get the answer. So what is the Landé's factor? Its formula is, J general formula is 1 plus S into S plus 1 plus J into J plus 1 minus L into L plus 1 divided by 2J into J plus 1. All the values I have here. So this is 1 plus S is 3 by 2, 3 by 2 plus 1. This J is 9 over 2, 9 over 2 plus 1 minus 6 into 6 plus 1 divided by 2 into 9 over 2, 9 by 2 plus 1. Can you calculate and tell me quickly what is this value? So let me do this. If you can do this faster, just tell me the answer. 3 by 2 times 5 over 2 plus 9 over 2 11 over 2 minus 6 into 7 divided by 9 into 11 over 2. How much this will be? 1 plus 15 plus 99 into 2 minus 42 divided by 99. So how much this is? Okay, this is 13 plus 99 minus 82 over 99. 1 plus this is 13 and this is 17. 20 30 over 99. So approximately this is 1.3. Right. How much you will get it? Okay, we'll proceed with that. If there is some mistake, you can check by yourself. So we will proceed with this. So we got G value, right? I'm not sure. I calculated it to be different in my calculation, but let's proceed with this. G is 1.3. You can check this by yourself. Maybe I have made some mistake. So G is 1 by 3. Then I have to calculate the magnetic moment for this atom Nd3, ionized atom Nd3+. So for this, what is the magnetic moment? The magnetic moment is G times J into J plus 1, but 1 root over is there. So G I have 1.3 and J I have, J is, oh, that's the mistake. It's 6 minus 3 over 2 is 9 by 2. Okay, 9 by 2 by 2. Okay, you can check. I can't find it now. Okay, J value is 9 by 2 now. 9 over 2. This is 9 by 2 plus 1, 11 by 2. So this will be 1.3. This is 1.3 by 2 root over 99. So this will be, let's assume to be 100, then 10 will come from this. So approximately I can say 0.13 divided by 2. This 1.3 is not correct, you have to check it, but I am proceeding with this. So this is 0.065. This is the magnetic moment for this atom Nd3+. What is this value? 0.065. And what is the unit? This unit is Bohr magnet. Right. You understood this, right? We need to find the magnetic moment for this ionized atom. For that, we need to find the Landesi factor first. Then we have the total angular momentum. We will put that and we will get the answer correct. And we were given the hint that the arrangement of the unpaired electrons like this. There were 3 unpaired electrons in F suborbit. So we arranged them in 3 suborbital and we got the L value, the total angular momentum, total orbital angular momentum, and we got the total spin angular momentum, like they are spin up states in three different suborbitals, so their spin will be add up, half plus half plus half, so this is 3 by 2. So we got L, we got S. Now it's time for the total angular momentum. So this total angular momentum formula, it depends on the arrangement of the unpaired electrons. If less than the half of the suborbitals are filled, then J form will be L minus S. If more than half, like if 4 of the states are filled, then the J formula will be L plus S, right? So we will get J value from this. So we got J, we got L, we got S, then we can put these all values in this lambda G formula, then we'll get G. We got G now, we have J, then we will put this in magnetic moment formula, then we'll get the magnetic moment, J into J plus 1. This is the procedure to calculate the magnetic moment. Right. Let's do the last one. The last one is CS3+, and this cesium atom also, it's ionized. 3 of the electrons were taken out from this, and its electron arrangement is like this here. You see, there is only one electron in the orbital. So let's do this for cesium atom, ionized cesium atom. So we have for cesium 3+, we have the electronic configuration as xenon configuration, xenon arrangement, and apart from that, one electron is there in F shell. So there are 7 suborbitals in F shell. 2, 3, 4, 5, 6, 7. So each with some definite L value. This is the quantum number for orbital angular momentum. So this is plus 2, plus 1, 0, minus 1, minus 2, minus 3. So as we are having only one electron, we will place this here. So what will be the L value now? As this is here, the L value will be 3. What will be the S value? Total, this is total angular moment, total orbital angular momentum. This is total spin angular momentum. As there is only one electron, so this value will be half. Now you see, less than half of the cells are filled. So what will be the J formula? J will be L minus S. So this will be 3 minus half. So this is 5/2. So we got L, we got S, we got J. Then we can calculate lambda G factor. G is 1 plus S into S plus 1 plus J into J plus 1 minus L into L plus 1 divided by 2 into J plus 1. You put all these values, then we will get G value as this is half into 3/2, then this is 5/2 into 7/2 minus 3 into 6 divided by 2 into 5/2 is 7/6. Okay, then I understood what mistake I did here. This is for okay, you correct it. This is 4 years, then accordingly we will get different value of land edge vector. Then we will put it and calculate the magnetic moment. So here equal to this 1 plus 3/4 plus 35/4 minus 6/35/2. So we will get some number. I am just not calculating it anymore. So we will get some numbers A. Then we got G. Then we can find magnetic moment as G into under root J into J plus 1. So what is J? 5/2. We have G from A, and this is 5/2 into 5/2 plus 1, which is 7/2. So this is A/2 root over 35. To solve this, you will get some A value and put this, and you will get the magnetic moment for this cesium atom, which is ionized, and this magnetic moment will be in Bohr magnet. Right? Any questions on this? Hello?
No, sir. Yeah.
What? I am not calculating this. It's very tedious. You can calculate this G value. I am just taking this as A. It will be some number. As I am not calculating, I am just taking it to be A. You calculate this and put this, and you will get the exact mu value. Right? You understood the process, right?
So can you show the options?
There are no options. This question is like this. You have to calculate this. You will get for the first term the G value will be 8/11 for ND. I am just telling you, just verify. G will be 8/11. This is for ND3 plus, and okay, I didn't calculate for the cesium. You can check the formula is same. Just check. And the magnetic moment for ND mu will be 12 over square root of 11 in Bohr magnet. To verify this.
Okay.
Okay, any question so far? No. You see this land edge factor, it's not 1. This contribution is coming due to the interaction between the spin of the electron and the orbital angular momentum of the electron. That's why we are getting a very different number from 1. This part is coming from spin orbital interaction. Right. Okay, so it's time for today. So we'll meet on next class. Right.